So let's talk about what I think is one of the most exciting features in modern Fortran, which is that as of the Fortran 2008 standard, Fortran is now a parallel programming language. Without any need to link to an external library like MPI or insert compiler directives like OpenMP, you can now write code that scales all the way from a multi-core laptop out to a supercomputer with hundreds of thousands of cores. We'll talk first about an explicit feature that is more coarse-grained, and that is the co-array feature that came into the language with Fortran 2008, which was actually published in 2010. And then we'll talk about a more implicit form of parallelism that also came in with Fortran 2008 and is also more fine-grained, and that's a loop concurrency mechanism. The co-array feature in modern Fortran requires that the compiler be able to start up multiple replications of a program referred to as images in what is generally referred to as the single program, multiple data programming style. One thing that's really nice about the Fortran standard is that it never explicitly states what an image is. One compiler team might map its images to MPI processes. Another compiler team might choose to map its images to OpenMP threads. A third compiler team, and this is actually what happens with the Cray compiler environment, might map its images or support its images with its own proprietary communication library. With Cray, it's DMAP. And that library might be able to take advantage of its proprietary interconnect technology to actually outperform these other technologies, MPI and OpenMP. In fact, some compiler teams might mix these or offer different technologies at different licensing levels, as happens with the Intel compiler, or on different platforms. Whichever technology is chosen, each image executes asynchronously. So that means if we take a snapshot in time, the images might be at different points in the code at that time. And this happens until either an explicit or implicit synchronization happens at the hands of the programmer. The most common explicit synchronization would be a sync all statement. If you're familiar with MPI, you can think of this as being like a barrier. Essentially, every image will execute until it encounters this sync all statement, and then wait until every image reaches that point. Memory allocations and deallocations are also implicit synchronization points. Co-arrays define a partitioned global address space, or PGAS, which means that as of the Fortran 2008 standard, Fortran now falls into the category of languages referred to as PGAS languages. The co-array data structure is an array data structure with two sets of dimensions, regular dimensions that appear inside parentheses, and codimensions that appear inside square brackets. When a program ranges over a regular dimension, the program is accessing data local to the image running the statement. When a program ranges over a codimension, the program is accessing global data across images. This allows for co-arrays to be a communication mechanism, and communication happens when one image references data on another image. One thing that's also nice that we can see here is that the co-array mechanism integrates nicely with the other features of the language. For example, you can take full advantage of the array features within Fortran, where 1:4 here is referring to all four elements as a block at once, and so we can access those elements as one block. So here I'm showing each image executing the same statement. On image 1, the statement copies the second element from image 2 into the first element of image 1. On image 2, the statement copies the second element from its own image into the first element on the same image. On image n, the statement copies the second element from image 2 onto the first element on image 1 on image n. Notice that we don't have to show the codimensions on the left side because they are optional. This has two important implications. First, it means we have a clear and simple way to know when communication is possible by noting whether square braces are present in a statement. That's important for performance reasons because communication is much more costly than computation. Second, it greatly reduces the burden of parallelizing existing serial applications. Statements involving coarrays with regular dimensions only need to change when communication is desired. Where communication is not needed, the legacy code stays intact. Now let's look at the loop concurrency mechanism that I mentioned earlier. It's do concurrent, and what this construct is doing is it's allowing me to tell the compiler that there are no interdependencies between passes through this loop. That exposes to the compiler an opportunity to optimize the code in various ways. A compiler team that desires portability without a great deal of low-level details about the hardware might exploit this construct with multi-threading or loop unrolling. A compiler team that knows more about the hardware might exploit it using vectorization. The last part of this statement here, you can see where I have what looks like an array reference where I'm referencing element I of this tau_p array. This could also actually be a procedure call as long as that procedure is pure. And in the functional programming video, I will talk about how to write pure procedures that can be called within a do concurrent construct. What we're seeing with do concurrent is one of the core philosophies of the Fortran language, and that is communicate properties, not optimizations. In other words, we want the programmer to be able to indicate to the compiler that there are certain properties like concurrency that the compiler might exploit, but we don't want to tell the compiler exactly how to exploit those properties. This facilitates writing code that is portable both to various existing platforms and to future platforms. Lastly, let's summarize some of the unique features of modern Fortran. There are other parallel programming languages out there, but they're not typically backed by an international standard. They're probably not as widely available. If you have access to the Intel compiler, for example, or the Cray compiler, you already have a parallel programming language in your hands. And oftentimes they're not platform agnostic in the ways that we've talked about here, leaving up to the compiler team important implementation details. And they may not be as scalable. There are published examples now of very complex production codes that scale beyond 100,000 cores using the coarray technology.